Okay, so this is going to be P4, section, chapter P4, continued, part 2. And we're going to have a part 3, so I'm going to talk about that in just 1 second. All right, so what's going to happen is we're going to talk about inverse functions today. We're going to introduce them. We're going to talk about some what they mean, how they should be used, how they can be used, and how to compute them. What's going to happen is we're going to be talking about the inverse functions for sine and cosine in Math 120 next week. And the problem with sine and cosine and tangent as well is that they actually don't really have inverses. They don't have inverses technically. And so there actually has to be some kind of considerations that we have to make when we actually talk about the inverses of sines, cosines, and tangents. So I'm breaking up this inverse function discussion into 2 pieces. So today will be the piece where we introduce it and we would talk about functions which have no problem regarding inverses. All right. And then next week in Math 92, we're going to talk about the situation where inverses do not necessarily exist, but you can do some sort of kind of consideration of your function so that a partial inverse does exist. Okay, and that will be applicable to trig functions. All right, so next week, one thing you should definitely do is watch the Math 92 lecture first, and then the Math 121. All right. For this week, order doesn't matter because we're just setting up the basics of inverses that we're not going to talk about until next. We're not going to use until next week in Math 120. All right. So inverse functions. So last week we talked about composite functions, and they're super, super, super important. If you are a STEM major and are going to be doing calculus in the future, composite functions are ridiculously important. Being able to break down a function into pieces. For example, those problems that you saw in the homework, write this guy as a composite function, right? Equals, f, sorry, let me call this guy h, equals f after g of x, where f of x would be, in this example, at square root x, and g of x is equal to x plus 1. This kind of breakdown is super, super important. So make sure you're very comfortable with it because a huge part of the computations in calculus depend heavily on being able to recognize how to break down a complicated guy into easier pieces that you already know how to work with. All right. For our class, we're not going to use inverse functions in this way as much. Our primary kind of reasoning for talking about inverse functions is, we're not going to be using, compositions in this way. Our primary reason for talking about compositions is so that we can talk about the concept of the inverse function. All right. Okay. So compositions are important in multiple ways. Okay. So what is an inverse function? Well, a function is something where you have an input and an output, right? So one example, the kind of most basic picture example is you have inputs here, you have outputs here, right? And kind of a very approachable example is your inputs are students. And your outputs are student IDs, right? 13579, 21111, 4743, something like that, right? And this function, I'm going to call it f here, perhaps. It's the function that associates each student to their student ID number, right? So maybe Alice's student ID is this, Bob's student ID is that, Eve's student ID is that right there. Okay. So this is a nice function. We can have functions that kind of look a little different. So let me do another one. So let me call this one G, and then output here. So let's say, again, let's put students on this side and Eve here. And maybe for the output, we put address, right? Let's say just a numerical address of where they live, right? 1423, 2117, and 47, for example. Okay, so maybe Alice lives on 1423 Main Street. Okay, let's say Eve lives on 47 Oak Street, something like that. But let's say Bob also lives on 1423 Main Street. Okay, so this is a perfectly legitimate function as well, right? Because given an input, you have an output. Given an input, you have the output. It's not a issue in terms of whether something is a function or not that Bob and Alice have the same output. Perfectly legal, right? For example, in terms of kind of more mathematical functions, the function g of x equals x squared, right? When you put in 2, you get the output 4. When you put in -2, you also get the output 4. Perfectly legal, all right? Now, what we want to talk about today are inverse functions, which means if you have a function like this f up here, I want to go backwards, right? So the function f is one where I input a person, a student, and I get the output student ID. Now I want to talk about the function that goes backwards, where the inputs are the student IDs and the outputs are students, right? The student who has that ID. Okay, so in fact, let me emphasize this by removing the input and the output in this picture. And let me just write over here student and then ID here. Let me do the same thing down here as well. Student, and this one was address. All right, so it's a more kind of generic picture. All right, so the backwards function, given an ID, I want the student who has that ID. So if I input 13579 in this backwards function, the output should be Alice. All right, if I input 21111, the output should be Eve. And if I input 47432, the output should be Bob. Okay, no problem, right? No problem in this picture. Everything is cool. All right, however, for this function down here, G, if I want to do the same thing, let's see what happens. So if I input, and again, I want the backwards function. So now I want my inputs to be addresses and the output to be the student who lives at that address. All right, so if I input 47, I'm going to get the output Eve. No problem. If I input 1423, now we got a problem. Because is the output Alice or is the output Bob? Right? Which one should it be? Okay, now if we think back at what a function is something where if you put in an input, you get a single output. And there should be no question or no ambiguity as to what that output should be, right? And here we have a question, right? 1423, should the output be Alice? That makes sense. She lives there, right, on 1423 Main Street. On the other hand, I could also say that Bob is a reasonable output because he also lives at 1423 Main Street, right? So because there's this ambiguity, that's not a legal function, okay? So the backwards function for G does not exist, all right? So it does not have a legal backwards function. All right, so already you can see this concept of a backwards function has some issues. And it's this backwards, the concept of this backwards function that we want to talk about, all right? Okay, so it's, in a way, it's a simple concept in that you're just going backwards. The output becomes the input. But in another way, it's complicated because some functions have major issues when it comes to this backwards function, all right? Okay, so today what we're going to do is we're going to only kind of focus on the situation where everything works, everything is cool, the backwards functions does exist, and uh, doesn't have problems. All right. Next week is where we talk about this second situation. And even though the backwards function does not exist, it's somewhat recoverable. Um, and we care about this because sine and cosine and tangents and the trig functions are actually all in the kind of category of the bad case. All right. So that's why I'm splitting into 2 weeks. Normally, in a way, in a discussion of inverse functions, you don't focus on the bad case as much. But for trig, we need to, because the bad case is the case that we're actually interested in, the trig functions. All right. So let's start. The backwards function. So backwards functions that's just a colloquial term. What we should actually be calling it is inverse function. Okay, so inverse function is the one that goes backwards. So I can talk about f of x and its inverse. All right, f of x. The words we say perhaps is f of x has an inverse function. Okay, so if we're in the first case up here, this case up here, then we would say f of x has an inverse function. All right. In the second case, we would say g of x does not have an inverse function. And again, we'll deal with that next week. Alternatively, you could say the words f of x is invertible. All right. Okay, so in terms of kind of these simplistic functions that I just talked about up here, with just these arrows and student IDs or whatever, kind of describing the backwards or inverse function is very straightforward, right? I just, take this blue arrow here and I flip it backwards, and that gives me my inverse function, right? That gives me the description of my inverse function. So instead of Bob going to 47432, it should be 47432 input goes to Bob as output. All right. So in words, it's also very simple. The input, what was the input for the original function, Alice, now becomes the output, right, for the inverse function. What was the output for the original function is now the input. So the input and the outputs are swapped. Okay. Now, the description and kind of this picture idea is very simple, but we'll see that kind of actually finding inverse functions is not necessarily so easy. And that's what we need to do in the situations where f is not given kind of in words or in a nice simple arrow picture, but rather in a formula. All right. Okay, but before we do that, we need to mathematically describe or define what it means to be an inverse function. Because just saying it's the thing that goes backwards or is the thing that flips the input and outputs is not precise enough for math. So we need a kind of more careful definition. And that definition involves compositions, which is why we talked about compositions last week. All right, so let me think about this. Let me give a name. So this good case up here, the student and the ID situation, we're calling f the function that has input students and outputs IDs, right? So what I'm going to do is I'm going to call h the function that goes backwards. All right, so h is going to be the guy. Let me do an arrow this way to indicate f is the function that goes from students to IDs, and h is the function that goes from IDs to students. All right, so h is the backwards function. Okay, so with this setup, f is the original function, h is the backwards function. Let's look at what happens if we do the composition. So if I do f first and then h second, so in other words, h after f, what do I end up with? So let's do it up here actually. So if I do f first, let's say with the input Alice. So, let me do it in this corner down here. Sorry about this. So f of Alice, right? And then I do h, so h of f of Alice. So this is the composite, right? This is h after f, h after f of Alice, right? That's going to be h of f of Alice, right? What is that? That's h of f of Alice is, Alice goes to 13579, right? What is h of that? H is the thing that goes backwards from 13579 to Alice, right? So this is Alice. Okay, and so what you notice is h after f of Alice is Alice. And if you do this with any of these others, you'll notice, of course, right, h after f of Bob is just going to be Bob. Because in essence, what we're doing is we're following the blue arrow first, and then following the yellow arrow right afterwards. So if I go blue to here, and then yellow back, I'm just going to end up back to Bob. Eve, I go blue to 21111, and then yellow back to Eve. Okay, now, so that means that the composite function always ends up outputting the same thing as what you inputted. Okay, all right, so that's the first point. Now, what happens if I do f after h instead? So in other words, I start from the ID side, I follow the yellow arrow, and then I follow the blue arrow right after that. So if I start with 13579, I end up going to Alice, following the yellow arrow, doing H, and then I do the blue arrow, doing F. I end up at 13579 again, right? Same thing with the other two. 21111, I plug it into H, in other words, I follow the yellow arrow, I get Eve. I plug Eve into F, in other words, I follow the blue arrow, I get 21111, right? I end up in the same place. So what we notice is for these backwards functions, or this inverse function, right? So if h is inverse function, right? Or let me write it kind of the more grammatical way that we say this. If h is the inverse of f, then what we notice is f, h after f ends up in the same place, and f after h ends up in the same place. So whatever input I put in, I get the same output, right? F after h, whatever input I put in, I get the same output, all right? So this is a very important kind of observation, because this essentially characterizes what it means to be an inverse, all right? So we need this characterization because we're not going to be working with arrows like this above here, this picture here. We're going to be working with formulas. So we can't just follow arrows back and forth in terms of a picture. We need to kind of have a more mathematical way of talking about the inverse. And this is that way. All right. So let me write the official mathematical definition. So if f of x is a function, and h of x is another function, then h is the inverse of f if exactly what we saw above, h after f of x is equal to x, and f after h of x is equal to x. All right. In other words, if you do f and then you do h, you end up in the same place that you started. You do h and then you do f, you end up in the same place that you started. Okay. So this is actually the definition of the inverse. This would be the mathematical definition, and it's motivated by that arrow picture that we just saw. Okay. All right. Notice that according to this definition, if h is the inverse of f, then f is also the inverse of h, right? So invertibility is kind of like a symmetric concept. If you're my inverse, then I'm your inverse as well. Okay. All right. So this is important because now I can mathematically check whether two functions are inverses of each other. For example, let's say we have, so now we're in the realm of actually working with functions. So let's say I have this, and then the idea is check that h of x equals cube root of x plus 1 is the inverse of f. All right. Okay, how do we check? We check exactly these two conditions here, right? We check if they're true. So the first one says I need to check h after f of x, and I need to see, is this question mark equal to x, right? If the answer is yes, then I'm okay. I can go to the next step, all right? If the answer is no, then I don't even have to bother with checking the second one because both of these have to work, all right? Okay, so is this true? Well, let me just write down what this means. On the left-hand side, this means, or let me actually do it kind of like a verify problem. So this is essentially a verify problem. So h of f of x, is this equal to x, right? That's the same as asking is h of f of x is x cubed minus 3. Sorry, x cubed minus 1. Is this equal to x? And then this is, h is the function that whatever you put in, I cube root, I add 1 to it, and then I cube root it. So x cubed minus 1 plus 1, like that, right? Because there's my instructions for h. Whatever I put in, I add 1, and then I cube root the entire thing. So here I'm putting in x cubed minus 1. So I need to add 1 to x cubed minus 1, and then cube root the entire thing. All right. So the question is this equal to x? And now we can actually do some computations. Minus 1 plus 1 cancel. So I end up with cube root of x cubed. Is this equal to x? And well, cube root of x cubed is x. And this one is yes, right? And so, of course, as usual, the way we kind of very technically argue it is because this is yes, then that is yes, then that is yes, then that is yes, that is yes, and that is yes. And so we can try the next step. All right. And let's actually do that. F after h of x, is this equal to x? Right? And you actually do have to check both because sometimes one will be true and not the other. All right, so this is the same as asking is f of h of x equal to x? And that's the same as f of, what's h of x? It's the thing that cubed adds 1 and then cubes root. So put that in right there. Is this equal to x? And then here, what is f? F is the function that you cube the input and then you subtract 1. So I'm taking the input, which is cube root of x plus 1, and then I'm cubing it, and then I'm subtracting 1, right? Is this equal to x? So here's where you really want to be very, very careful in terms of plugging in functions and working with kind of plugging in complicated things into a function. Oops, that's a cubed right there. Okay, now we've got cube root, cubed, so those cancel. So I just get x plus 1 minus 1. Is this equal to x? And obviously, that's okay. X is equal to x? Yes, right? And so up here is yes, 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 yes. And so we've confirmed, right, both this one here and we've confirmed this one up here. And so that verifies that f of x and h of x are inverses of each other. Okay. All right. So, despite the fact that kind of the picture idea is very simple, in terms of formulas, where we don't have kind of that nice arrow picture, things look a little bit more messy, but in a way they're still straightforward in that you're just plugging in, right? F after F, F after G. Okay, a bit of notation. If F and H, so let me write like this. If H is the inverse of F, we use the notation F f inverse of x equals h of x. So this is the notation for the inverse right here. All right. So that's when you see f to the minus 1 of x, that means the inverse. Okay. So very importantly, this to the minus 1. So normally when you see it to the minus 1, like if you have 3 to the minus 1, that means 1/3, right? That's just for numbers. So for functions, f to the minus 1 does not mean 1 over f. It means the inverse function. That's purely notational. So be very careful about that. All right. So in short, when two things are inverses of each other, then you have this and you have this. All right. Okay, so we'll try to stop using the f and h and instead use f and f inverse, right? So normally we say this as f inverse or inverse of f, but f inverse is perhaps more commonly said. Okay, so a couple aspects of the inverse that are really important. So first of all, now that we're working with kind of complicated functions, complicated functions have complicated graphs. Let me look at a function f of x, and let me say its graph looks like something like that. All right. Okay, so the question is, so this guy has an inverse. All the functions we're talking about today are going to have an inverse, and I'll talk about an example where of a function that doesn't in just a couple minutes. The question is, what is the graph of its inverse function, right? So f inverse of x, what does that look like? And the good news is, if we know the graph of f, then the graph of f inverse is actually really easy to figure out. And the reasoning behind this is that just from our very first example, the inverse function is the thing that goes backwards. So outputs become inputs and inputs become outputs for the inverse function, right? So for example, this point right here, let me just make up some numbers here. For example, if this is 1 and that input of 1 gives me the output of 5, let's say, right? So this is f, right? So what would the graph of f inverse look like? Let me do that in blue. So f inverse, actually let me write out what this means right there, right? The meaning of this picture here is that f of 1 is equal to 5, okay? Well, f inverse is the function that goes backwards. So if f of 1 is equal to 5, that means that f inverse of 5 is equal to 1. Okay, it goes backwards, right? And of course, if this is the case, right, you can see the composite function is just going to be x, right? Because if I do f of 1, I get the output 5, and then I follow that up with f inverse of 5, I'm going to get back to 1. Okay, so kind of colloquially, the input here is 1, and that becomes the output for the inverse. The output here is 5, that becomes the input. Okay, and so what that means in terms of the graph of f inverse is that when I plug in 5 to the inverse, when I plug in 5 to the inverse, I'm going to get the output 1. So right there. All right. So this point here represents the fact that f inverse of 1, sorry, I said 5 and 1, sorry, I drew it in the wrong place. I guess I need this erased here. And it's right there, right? This point here represents the fact that f inverse of 5, right? Input 5, output minus 1. Output 1, sorry. Output 1, not minus 1. Output 1, right there. Okay, sorry about that. So this represents f inverse of 5 is equal to 1. Okay. All right. So what was the relationship between this point and that point? Well, the coordinates here was 1, 5, the coordinate here is 5, 1. So they're swapped. The x and the y coordinates are swapped. Okay, so that gives me a huge hint as to what the graph of f inverse looks like. For example, right there, this point represents the fact that when I input 0, I get the output maybe something like 4, right, for f. That means when I input 4, I should get the output 0 for f inverse, right? So the point corresponding to that guy for f inverse should be something like that, right? When I input 4, I get the output 0, right? And again, in terms of coordinates, this coordinate is 0, 4. So therefore, the coordinate corresponding to it is 4, 0, all right, for the inverse, okay? So if you think about this a little carefully, what you'll realize is if you draw the line y equals x here, then the graph of f of x, if you flip that across the line y equals x, if you reflect it across y equals x, then you'll end up with something that looks like that. And this flip across y equals x exactly flips every point. Let me call it x comma, or let me call it a comma b here. It flips it to the opposite side right there, b comma a, right? So what that means is the graph of f inverse is just going to be the graph of f, except flipped across y equals x. All right, so this guy here is the graph of f inverse of x. Okay, so that's my reasoning for why it is. This picture that I've drawn is fairly simple, but you can have a complicated situation where f of x perhaps looks like that, right? And then when so let me write this. This is graph of f. Then when I flip it, it's not going to be. Let me exaggerate this a little bit, just to emphasize my point. So if this is the graph of f, and if I draw the y equals x, the graph of x is on both sides, of f is on both sides, right? But when I flip it, what happens is the stuff on the right of y equals x, let me emphasize this y equals x, the stuff on the right of y equals x flips to the left, the stuff on the left flips to the right. So this bit right there flips to here, all right? And it should be like a mirror. And then that bit right there, oops, that bit right there flips to here. Okay, again, like a mirror to the other side. All right, so in the end, the graph of f inverse looks like that. Okay, so the flipping can be a little messy if your original function crosses the this diagonal. All right, notice, of course, on the diagonal, they touch, right? The two graphs touch. And that's because when you're on the diagonal, y equals x, this is the point that has the same x coordinate as the y coordinate, right? Because literally y equals x tells you that. And so what that means in terms of the graph of f is that f of a is equal to a, right? Well, if f of a is equal to a, then f inverse of the output a should be equal to the input a. So f inverse of a should be a as well. And so the two graphs, should in all reason intersect right there. And of course they do. Okay. All right. So this will be very important. For example, in pre-calculus, when you talk about exponential functions, the inverse of that is the logarithmic function, the logs. And generally, the way you learn this is you know the graph of exponential, and so therefore you automatically know the graph of log, all right, by flipping it across this y equals x. All right, this is going to be super useful for us because this is exactly how we're going to draw the graphs of the inverses of our trig functions. All right, again, after some sort of consideration because our trig functions have some issues. All right, so actually let me talk about some issues right now. Let's say we had a function that looked like, let me use white. So let me say I had a function that, let's say I had a function that looks like this, right? If I try to flip this across y equals x in order to get its inverse function, let's think about what we get as the result. So what happens is this bit right here flips to something like that, right? So again, this diagonal line is to be thought of like a mirror. And this second bit, this bit over here, flips to the other side. That looks something like that. All right. And again, it's supposed to be kind of symmetric. Maybe I didn't draw this that well. Let me fix this a little bit. Oh, that's even worse. Right, so it's supposed to be symmetric where this point is right on the opposite side of that point. This point is right on the opposite side of that point. This point is right on the opposite side of that point, and so on. Okay. Now you can kind of see a problem here. This red guy is supposed to be the inverse, right? But you can see that if I draw a vertical line right there, for example, for the inverse function, this input corresponds to that output and that output, right? So this function here is not going to satisfy, this inverse function, the red one, is not going to satisfy the vertical line test, or this graph is not going to satisfy the vertical line test. So it's actually not a legitimate function. And so my original function here, f, does not have an inverse, because if it did, its graph would not be legal as a function, right? So that means that this is, in terms of pictures, this is a function f has no inverse. All right? Because its inverse would not satisfy the vertical line test. Because its inverse, given an input, there could possibly be multiple outputs, which is the only illegal thing to have when you're talking about a function. All right, and if you think about this a little carefully, this yellow vertical line actually corresponds to this horizontal line right there, right, when you flip it. And so what's happening is, if your original function fails the horizontal line test, right? So in other words, if a horizontal line touches your original function in more than one place, then what's going to happen is when you flip it, your inverse function, or your proposed inverse function, is going to fail the vertical line test. And so that means you're not going to have an inverse. Okay, so in terms of pictures, in short, if your original function f of x fails the horizontal line test, so if your original function looks like this, which is of course something like a sine function, right? You have a horizontal line here, touches at multiple places. What that means is it's not invertible. It's not going to have an inverse, all right? Because it's going to have actually many inputs. The inverse is going to have many inputs that have many outputs, right? Or let me say it this way: your inverse, your proposed inverse, is going to have situations where one input corresponds to many outputs, which is totally illegal, right? So now we know, right? We can literally see sines and cosines definitely are going to be a huge problem for us in considering inverse functions. All right. On the other hand, of course, if your original function looks like that, where every single horizontal line touches just once, right? Touches once, touches once, touches once, touches once, or 0 times. It's certainly allowed to touch 0 times. So maybe down here it touches 0 times. Then it does have an inverse, because what that means is when I do this flip across the y equals x, it's only gonna, the horizontal lines become vertical lines, and so the vertical line test will be okay, and so the inverse will be legitimate. All right. So in the homework for this week, you'll be asked to, you'll have a function, you'll be given a function f, you'll be asked to graph it using the graphing techniques that we've learned over the last few weeks. And then you'll be asked to graph its inverse function. And this is exactly how you want to graph its inverse function, by graphing the original function, drawing y equals x, and then flipping it across. All right. Okay, super useful because, like I said, that's how you're gonna learn how to graph logs from exponentials. That's how next or soon, when we talk about inverse trig functions, how we're gonna graph the inverse trig functions, arc sine, arc cosine, and arc tangent, and so on. All right. The last topic we want to talk about is, again, so we just talked about the picture, right? How would you get the inverse of f if you had the picture of f, right? This is f. Automatically, I know the picture of f inverse. Let me extend this over here. Automatically, I know the picture of f inverse is like that, right? But what about if I don't have the picture of f, right? What if I only have a formula for f? So what if I say f of x is equal to, let's say 3x plus 7, right? What is f inverse of x, right? And here, we're not going to be giving you functions that don't have inverses for this section. So when I ask this question, it's not a trick question as in there is no inverse. There actually is going to be an inverse, all right? And so the question is, what is its inverse? How do we figure it out? Well, luckily, we can use the same concepts to figure out the formula for the inverse. And the idea is like this. So when I write f of x equals 3x plus 7, let's actually convert this to a formula in terms of x and y. So y equals 3x plus 7. Let me rewrite it like this. And here the kind of thought is that y represents the output of f, and then x represents the input of f. All right? Okay, this makes it a lot easier to do what my next step is. And also, thinking of it this way with the y and the x also relates to the graph, because x is the x coordinate. You can think of it this way. X is the x position, y is the y position, and this would represent a point, right? X comma y represents a point on the graph of f. Okay, now what about f inverse? If y is the output of f and x is the input of f, then f inverse, everything is swapped, right? And so this guy would be, for f inverse, this would be the input of f inverse, and that guy would be the output. Let me do it over here. X would be the output of f inverse, right? Because f inverse, again, very, very importantly, it swaps the inputs and the outputs, all right? For example, without doing any computations, I know right here, or very little computations, I know that f of 1 is equal to 10, right? 3 times 1 plus 7. So automatically, I know f inverse of 10 is equal to 1, because swapping the inputs and the outputs. Okay? So what we're gonna do next is this formula here represents f, right? Y is the output, x is the input of f. So now what I'm going to do is I'm going to switch to the world of f inverse. I'm going to swap x and y. All right? So that's going to become x equals 3y plus 7. All right? Now when I swap x and y, what that represents is now y is, what was the input of f inverse was y, now becomes, let me say it like this. Y was the input of f inverse. Y is the output of f. When I swap x and y, now x becomes the input of f inverse, and y becomes the output of f inverse. All right. So in a way, the way to think of this is this is the equation for f. When I swap x and y, that's the equation for f inverse. All right. Again, because inputs and outputs are being swapped, and that's literally kind of what it means to do the inverse. All right. Okay, now this is the equation for f inverse, but we like to express everything in terms of the output equals blah, 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 right? And that's not how it is here, right? X is the input, y is the output. It's all mixed up. So what we want to do is we want to solve for y. All right. So when I solve for y, I'm going to get subtract 7 on both sides, x minus 7 equals 3y. And then divide by 3 on both sides, I get y equals x minus 7 over 3. Okay. And again, once we swap the x and y, this critical point right there, right, when I swap the x and y, that moves from the world of f to the world of f inverse. And so this formula here is now the formula for f inverse. Okay. So f inverse of x is equal to x minus 7 over 3. All right. So this is how you calculate the formula for f inverse. And as usual, you can always check your answer, right, by calculating f after f, or what you thought was f inverse. And you can check, is it equal to x? You can check this guy here, is this equal to x, right? So in other words, do the composition of this, this function here with this function here and see if you get the correct outputs. All right. Okay, let me do another example. So for example, let's say f of x is equal to x plus 1 over x minus 3. All right. So find the inverse. So what do? Our step 1 is to represent this function in terms of x and y. So y equals x plus 1 over x minus 3. Okay, and here, this formula represents f, right? So this is f. Let me write it like this. This represents f. Okay, now I swap x and y. X equals y plus 1 over y minus 3. All right, everything that was x now becomes y. Everything that was y becomes x. All right, so swap x and y. So now this represents f inverse. Okay, because again, you're swapping the input with the output, right? And that's literally what the inverse function is, right? The inputs become the outputs, outputs become the inputs. Okay. So now we just solve for y. Now solve, for y. And that will give me the formula for f inverse. Sorry, this is a little messy here, f inverse. So in this case, the algebra is a little more difficult, but it's still algebra nevertheless. This is y minus 3, multiplying to y minus 3 on both sides. And I guess here I want to distribute it in. And then I want to isolate the y, so I'm going to throw all the y's to the left side. And all the x's, or this minus 3x, the terms that don't have the y's, the terms that don't have the y's to the right side. And then again, I want to isolate the y's. And I end up with y equals 3x plus 1 over x minus 1. All right, so once I have y equals something in terms of only x's on the right-hand side, then that's my formula. So f inverse of x is equal to 3x plus 1 over x minus 1. And again, you can check by taking the composition of the guy I just found with my original function to see if I end up with just x. If I do, then I'm all set. All right. Okay. This week, you'll be doing a few of these problems. Next week, we'll have you do a few more of these, just so that you get comfortable with it. Okay, by the way, I promised you that the functions we give you this week, these all have, like if the book says find the inverse, it actually legitimately has an inverse. One thing to think about is what would happen if I gave you a function and I tried that did not have an inverse, right? And we tried this procedure. So what would happen is somewhere, down here when we're doing our calculations, we'll end up with y equals something, but there'll be some sort of ambiguity here as to what y should be, right? We'll talk about this more in depth next week, but that ambiguity reflects the fact that the function has no inverse, all right? So you can actually detect whether a function has an inverse or not by going through this procedure and seeing if you successfully get a nice formula at the end, right? So here, this is a perfectly legitimate formula, right? For example, what will happen in some bad cases is you'll end up perhaps with y equals plus or minus square root x minus 1, right? That's going to be no good because that means you've got an input x corresponding to two outputs, right? The plus version and the minus version. So this actually can also detect whether you have an inverse or not. Okay, again, there's only a few of these kinds of problems on the homework for this week. You'll do more of them next week just to make sure you're comfortable with them. And also next week, we'll talk about the situation where you don't have an inverse, but you can somewhat recover from that. And that's literally what's going to happen in the situation of all the trig functions. All right, so this section was a little long, or this lecture was quite long, but I cannot overly stress the importance of inverse functions. You always would like to work with functions that have inverses, and you're always unhappy if the function that you're working with does not have an inverse. Because being able to go backwards is really, really useful, whatever the problem is you're working on. And again, if you don't have an inverse, you're not able to go backwards. And that causes just a huge amount of problems. And we'll see that, of course, for the trig situation.